Awesome. So Bob gave such a great introduction. So I'm going to talk about towards all-terrain locomotion with millirobots, but I thought I'd just focus on one of them, which is Salto, which Bob already introduced. So what do we want to do? So those squirrels look pretty compelling as a challenge for locomotion. And how about a lot of other things? Their saltatorial just means jumping locomotion. So you can imagine something like leopard jumping between rocks, jerboa down in the lower left, chinchillas, and lots of things jumping around. So is the mic working? I think so. Oh, I just need to be closer. It says stay back 10 inches, but 10 inches not so good. Okay. Great. So we're thinking, like, how do we achieve these types of behaviors? And we have to come up with a metric. And the metric we came up with we call the vertical jumping agility. Yeah, a little closer? Okay. Yeah, the metric we came up with we call the vertical jumping agility. So we can have lots of things that just jump by winding up a spring, but if you want to be able to maneuver on high slope terrain, you need to have a high repetition rate. So the metric we're looking at is just the ratio between how high you jump and how fast you can do it. Because if you can do that really quick, then you can go off of vertical surfaces like in parkour. And so this is what we mean by vertical jumping agility, going quickly up a surface like that. So we looked at a bunch of animals and robots, and we plot them in the space where we look on this axis is just the jump frequency, how fast you can jump, and the vertical axis is how high each jump is. And of course, there's a ballistic limit there where you can't jump any faster than it takes to fall down. And here you go. These are the wind-up jumpers, and I put on there and there's the ones that are running around like MIT Cheetah. They'll be running pretty fast, but not jumping that high. And here's one we made. We talked about that last year. The jump up to 2 meters in height. And I put Atlas on there, saw that in there. So it's actually pretty good, but it's down here. But what's up in this category up here? Well, that's interesting. That's this animal called the Galago, which could jump has a jumping agility of greater than 2 meters a second. And so we said, okay, well, what can we do in terms of a robot to get up there? And that's this Salto robot, which gets not quite as good as a Galago, but still way up there. So what's involved in making something like this? We've got 4 key design principles. One is the series elastic power modulation, so you can store energy in a spring, but not wind it up, but be able to release it very quickly. A design which allows you to have a mechanism which moves in a straight line, so you can jump straight. Something give you maneuverability, so you can maneuver around, change your orientation at will, and this high power density is also very important. Turns out there's an animal inspiration for this. There's tricks that an animal uses, which can have a tendon wrapped around a joint, which allows it to get more instantaneous power out of the muscle than it can happen statically. And there's a lot of clever design issues here in making a mechanism which is very well suited for the motors. So the motors, as they speed up, they have less torque. So you can design a mechanism that gets your motor running very close to its peak power over most of its stroke. And this is some clever work by Mark, who's sitting there for that design. So a little bit about how the mechanism works. As a motor goes through a gearbox, there's a spring here. This is your series elastic element, which then drives through the mechanism and causes this thing to accelerate. So here's the crouch position as the motor winds up, stores energy in the spring, and then this is all released. And we have a very short contact time on the ground. It spends something about a tenth of a second or less on the ground, and most of the time is in the air, which gives us very interesting behavior, as Bob showed. So this is a 2-jump. This is from last year. This is just in the plane, so it can jump, and this was where your vertical jumping agility comes in. It can hit the surface and do another jump. If it's wind up, it would just go up and then fall and never be able to do that second step. Okay, and just once more. Okay, jumps. And I should mention it's got a peak acceleration of about 14 g. So gravity's only 1 g. So whether you're on a ceiling or on a wall, it's sort of plus minus 1 g out of 14 g. It doesn't really care, which is kind of interesting. The control on this is a main leg control, and then we add on two props, which give us the ability to control the roll and the yaw, and a tail, which you can see here in the picture. This tail which rotates, which gives you pitch control. We don't have onboard control yet. This is all through a motion capture system. But let's show you some of the data. Here's again the robot with the thrusters and mechanism. We're looking here at the roll, pitch, yaw, and you can just see it's bouncing around the room. The thrusters are, you'll see in the video, the thrusters get it to the point where it's just saturating so it doesn't tip over. This is the tail controlling the pitch. Should mention the vertical bars here where it's making contact with the ground, and there's your tail duty cycle, get a little saturation. So let's watch a couple of these. This is moving around, and one of the interesting things related to an earlier talk is that if you have sufficient control authority, the amount of planning you need to do actually goes down quite a bit. So this doesn't really care what surface it's on. It's just triggered whenever it hits the ground to give a big bounce. And you can see it goes up on these surfaces without any problem. And there you go. Okay, and the next one we'll see. So it comes back, and that's all controlled. So it's steering around, basically doing a rectangle, and those objects are in there. It doesn't really care. Let's look at another one, and let's see if we get a little, if there's any sound on this, but this is the animal, which is our inspiration, so we're a bit away from being able to do what that animal can do. I'll run this other one at the same time. Again, it's going around in a rectangle, this time have a little bit bigger obstacle that it's got to bounce up onto. And it just doesn't, it just keeps on going. It's directed, as I said, with the external motion capture system, goes around, comes down. So just to see what is this actually doing as it's going along, you can see these, it's bouncing back and forth here. The horizontal CG is going about a couple meters back and forth, going back and forth here. If you look at where the velocities actually are, it's putting out here peak horizontal velocity close to 3 meters a second. So in a single jump, it can go from stationary to a 3 meter a second horizontal jump. One of the things that's critical in this is the friction cone. So as Bob showed in the video earlier, if you're outside the friction cone, bad things happen. So working a lot on trying to understand how we can come up with a mechanism that will engage the surface. So even though we have 14 Gs, unless we have a wide enough friction cone, we'll start to slip. And so this is a passively engaged spine that'll dig into the surface and give us good ability to have a much wider friction cone, which will then give us access to more and more surfaces. So where do we want to go from here? So bouncing around horizontal surfaces, there's already some planning work out there, Jean-Paul Lamond, of going on vertical surfaces. Basically, our robot is sort of like a point mass that can have high acceleration, so we can go on these surfaces, horizontal or vertical. Eventually want to go into these sorts of things, jumping between branches, which means we need to understand on the compliant surfaces, very much like what Bob showed. Great. So with that, I'd want to just acknowledge certainly the group of students who put this amazing robot together. Thank you for your attention.
Thanks, Ron. I'd like to invite Mark to set up. Is there a quick question for Ron? Going once, going twice. Okay, thank you. Our next speaker is Mark Adosi from Stanford.
So I thought for this year's edition of BARS, I would talk about something for a change that has nothing to do with gecko adhesives or spines or climbing or perching. We've had a different project going on for several years with a radiologist at Stanford Hospital, Bruce Daniel. And the basic idea is to take the MRI machines, which are becoming increasingly popular as an imaging modality, and to do interventions, to do procedures while a patient is inside the bore. But as you can see from the photo on the left, there's a problem there. It's a very narrow tube that the patient is in, and the physician has to stand outside. So the way procedures tend to go today is something like this. You have an initial scan, and then you take the patient out, and you insert a needle, and then you put the patient back in, and you discover that the anatomy is shifted or the needle deflected, and so you take the patient back out, and these procedures can take 40, 45 minutes. So our vision, there are various things you could do. You could have a robotic system or whatever, but our vision is to have a teleoperated system where the physician is able to stand outside, look at a screen, see real-time MR imaging, and perform procedures and have those correspond to operations that take place under live guidance in the MR machine. So it's an interesting challenge, and the way that we're proposing to address it is in three parts. The first is to have a passive teleoperated system based on rolling diaphragm actuators. At the moment, I'll say more about that later. And then what you'd really like is for the physician to feel like her fingertips are there, right there at the tip of the tools. And so we're using instrumented tools with optical fibers, and then finally a haptic display based on on electroactive polymers. All right. Well, so the first part is this rolling diaphragm actuator, and this actually started a couple years ago. I was visiting Carnegie Mellon, the Disney labs at CMU, and talking with Peter Whitney, who was using these very nice hydrostatic transmissions for human interaction robots. So you do the controls, and the robot moves, and the forces and motions are reflected in both ways. And they have some nice advantages. There's no sliding seals, so there's basically no Coulomb friction. They're very stiff. There is some hysteresis, but you know what? Viscous damping and hysteresis, people tolerate that much better in a system. So what Peter's made is a very clever system with two of these actuators wrapped around a timing pulley to turn it into a rotary actuator. So that's part one. And the best of these rolling diaphragm actuators today they're from Japan, and the problem is that they're fairly short stroke. So what we've done is we've set up a kind of a clutch thing where you can push the needle in. It's just like when you pick your mouse up and put it back on the pad when you're trying to do like a big CAD model and your mouse pad isn't so big. So you go partway in and you reset, and then you keep pushing the needle the rest of the way in. And there are some forces. There's a little bit of friction, not in the transmission, not in the actuator itself, but in the cable capstan transmission and other parts, which we'd like to minimize. And then, as I said, there's some viscosity and some inertia, which you'd like to minimize. Nonetheless, you can ask yourself, with this kind of a teleoperation system, what can people do? And in particular, could you detect the light force that occurs as a needle just starts to puncture a membrane? And so we did some tests on that with a one-DOF system, and the answer, well, somewhat, 77% success rate. Well, that's because inevitably you have some inertia. So it's not like holding the needle in your fingers and pushing it in. What it's like is holding a needle in a pair of tongs and pushing it in and seeing if you can detect membrane puncture. And that's the motivation for the sensing and the haptic display. So ongoing work is to go to multi-degree of freedom systems for things like liver biopsy, some nice mechanisms you can design there. All right, so let me go to, oh yeah, and one other thing is I mentioned that the diaphragms have a very short stroke. Well, do they have to? It's a manufacturing limitation, but could you make special custom diaphragms that had a much longer stroke? Then you wouldn't need any transmission. Then you would eliminate some of the undesirable effects. However, it's tricky. You have to have very thin to minimize hysteresis. You want it to be very stiff in the axial direction, but not so stiff in the radial direction. And so there's a student, Alex Grubly, who's working on just that problem. And I wouldn't say we're quite there, but we're getting close. And they feel good already. And so I hope to have some new results on that very soon. So let me turn now to the last part, which is the display. And let me get on to the next slide. There we go. As I said, what you really want to do is also feel small forces that would be relayed back to the physician's fingertips. So we've been working with optically instrumented tools. These are optical fibers. You micromachine grooves in the inner stylet of a needle. You have fiber Bragg gratings. They're very accurate optical strain gauges. And then we micromachine little holes at the tip of the needle. That gives us a better sensitivity to axial forces as well as bending. And for display, what we're using is skin stretch, which is something that we've done on and off for years. It's nice because skin stretch, unlike vibration, gives you a sense of force and also direction. So when you pick up objects, when you're handling objects, a lot of how you tell how heavy those objects are is lateral deformation of the skin due to the Meissner corpuscles and Merkel ending. So we have a display. It has to be MR compatible, of course, so we're using electroactive polymers. And to get the force level up, we use a 6-layer display for this very light handheld display. And as you can see, it matches pretty well the forces at the tip of the needle. There are some tricks you have to do. This is a very viscoelastic material, so when you hit it with a high voltage, it responds initially pretty fast, but the relaxation is slower. So we're doing some we have a special circuit to do some kind of fast discharging to relax it more rapidly. And the other thing to be aware of is that the latency, end-to-end latency, you have to minimize it. So this is from when a force first hits the tip of the needle, goes through the optical interrogator, goes through the EtherCAT, goes through the amplifier, goes into the haptic display. How short can you make that total time? And we're getting it to around 28, 30 milliseconds for the force ramp up. And that's actually plenty good that people don't notice the delay. So when you repeat the membrane puncture experiment with either naive subjects or with interns who've had some experience with needles, now we're getting, it's very obvious when you've hit the membrane. It's around 98 or 99%. So there's a lot more that I could say about these, but we're going to run out of time. Just to summarize, the three main components are, first of all, working on long stroke rolling diaphragms. I think of it as a kind of selectively soft robotics. Soft where you want it, but stiff where you want it not to be soft. Optically instrumented tools, and then finally the electroactive polymer displays. So thank you very much.
Thank you, Mark. Our next speaker is Alice Logino from Berkeley.
Sorry, trying to connect. Ah, okay. Hi, the slides will show up any second. Okay, my name is Alice Egagino, and I'm going to talk about tensegrity robots for space exploration and more. Our motivation for considering tensegrity robots is we wanted to investigate their mechanical properties for being able to handle heavy stresses and have a tension network. But the compliant nature of the robot allows us to put a payload somewhere inside the robot, maybe throw it or drop it or have it hop long distances and survive with the payload in the center. And it also is able to, we hope, and that's something we want to show you, transfer rough terrain in ways that, say, some wheeled robots wouldn't be able to handle, and maybe in hazardous areas. So what is a tensegrity network? Well, the simplest tensegrities are all axial components. They either have compressive stresses or tensile stresses. They are very strong relative to their weight. They minimize stress concentrations because the loads are immediately propagated throughout this tension network. And they have a tunable stiffness structure. So we can actually tighten the tensegrity robot so it can be as stiff as we want it to be through motors that control the wires. So we worked with NASA Ames with a project that they had going to a moon of Saturn called Titan for space exploration. But then we submitted a proposal for early stage innovation to go to the moon and to be able to launch out of a rover. We'd be like a secondary rover or a probe, and that we would be able to carry a 1 kilogram load on a probe that weighed 10 kilograms or less and deliver a 1 kilogram payload over 1 kilometer of distance on the moon using this simple gas thruster, say a neon thruster. And so you can see some of the pictures here of a 6-bar tensegrity, and here's an example of a 6-bar tensegrity. It could be flat or relatively small when it's being stored within the rover. It can pop out, have the cold glass thruster in the center, and as you can see here, it might deploy from the rover itself and then make several hopping motions. And then the challenge is then how do you locally get more precise motion in terms of traveling on the surface of the planet. Now, we know that we can survive going down craters. The question is, can we go up a crater? And that's what I'm going to talk about, our ability to walk up slopes. Here's an example of path planning on one mission that we might have on the moon. We've got a simulation of the surface of the moon. And so what we might do is use the cold gas thruster to get out of the rover. We land on the planet. We have to orient the tensegrity robot so it's in the direction that we want it to go in terms of reaching the target. We have another hopping motion or several hopping motions, sort of like when you play golf. You want the long stroke, and then when we get close to the target, we want to have more of a putting sort of motion and rolling motion. Now, one thing we discovered is that going up craters takes a lot of energy, is difficult. We wanted to make sure that we could reach at least a 30-degree slope, which is what was required by our ESI grant. So we started out with, we have a whole range of tensegrities, by the way. We have about 6 different prototypes that we use. We thought we would start on our smaller tensegrity robot because we're able to reconfigure it very quickly. And we thought we would try could we go uphill if we just actuated a single cable and then move up to a higher cable actuation. So on this simpler robot, these 6-bar tensegrity robots have 24 cables that we could tighten or loosen. In this particular one, we are under-actuated. So we only have 6 motors and 6 cables that we can control. It has a central microcontroller and 6 of the motors. And the orange stuff you see isn't really an elastomer that we use or we control. It's really to keep the tension network and make the prototyping easier. So looking at the single cable as a baseline, using our simulation software called the NASA Tensegrity Robotic Toolkit, and Vitas is over there. Sunspiral helped develop that software, and I'm very happy to work with him on this project. You can see that it kind of moves by going up the slope with a kind of zigzag motion, but the highest slope we could handle with only a single cable actuation was about 13 degrees. So then we looked at, okay, what could we do with 2 cable actuation? And we developed 2 forms of cable actuation. One is what we call simultaneous, where we tighten up one cable at the same time we might loosen another cable. The way these robots work is by shape shifting, and we're changing the center of gravity so it can kind of flop over, what we call punctuated rolling, and then we take the next step. Or the alternating actuation is one where we only take a step at a time, or we only actuate one step at a time individually or sequentially. And so this is what we found in physical experiments that we've actually run on the system. One is the alternating allowed us to go up the highest slope so far, which was 24 degrees, but very close to the simultaneous actuation. But what's important is that the simultaneous actuation, not surprisingly, was almost twice as fast as a single actuation or the alternating actuation. And the reason is that we're performing 2 operations during the same time rather than doing them sequentially. So that kind of makes sense. And you can see them here being compared, the single cable actuation at the top, simultaneous actuation in the center, and the 2-cable alternating actuation at the bottom. And the simultaneous one can go about 6 centimeters per second on a flat surface. And I note that the Mars Curiosity rover goes around 5 centimeters a second. So it may seem slow to you, this is sped up, but in planetary exploration, we don't necessarily need to be that fast. Here's an example of it actually working in the hardware. on a slope, and the thing to watch here is what's happening to the center of gravity, or the center of mass. So with a single cable actuation, the mass is rising fairly high up. Of every step, there's some energy that goes into pulling it up that is in a sense a kind of wasted energy or can make it unstable. With the simultaneous actuation, note that the center of gravity is very low to the surface. And we think that is part of its success strategy in that it is efficient in energy, but also is a much stabler type walking gait. We're interested in been working on a number of different walking gaits, by the way. We've used simulated annealing, we've used various stochastic processes, genetic algorithms to come up with different combinations of strategies. We're also looking at deep learning and model-based control, and Brian Serra is going to talk a bit about this during his lightning talk. And Andrew Sablehouse will talk about our quadruped tensegrity robot. So indeed, if you actually look at the center of gravity, you'll see that the green plots are the simultaneous actuation. They are the lowest to the ground, and the highest is a single cable and the alternating actuation. We've tried the robot on rough terrain, including actual simulation of moon dust. And so in summary, we are on track to meeting our NASA requirements. We've demonstrated uphill locomotion with spherical tensegrities. We can, with single actuation, go up to 13 degrees, two cable actuations, 24 degrees. Our goal is to get to 30 degrees, and we think we can be on target to doing that if we had full actuation. So we're moving up the number of actuators we're going to use. We're going to continue looking at deep learning to try to understand some meta-control strategies along with model-based control. And we want to look now at the spines that we would use as end effectors, because as you saw, there was some slippage in the system. We think we could get a lot more traction if we had spines. So our next step also is we're starting a company called Squishy Robotics to the rescue. And so we feel that these same robots, because they can carry a payload in the center, could be dropped from a UAV and be used for disaster rescue before first responders get there. So in summary, let me thank our team at the BEST Lab and the early stage innovation grant that we have from NASA Ames. Thank you.
Thank you. Our next speaker is Max Schwager from Stanford.
Hi, everybody. Let's see if this works. All right. How's my volume? Is that good? I can't see anybody, so I'll assume it is good. The lights are bright up here. Okay, my name is Max Schwager. I'm from Stanford. I'm interested in multi-robot systems. So this means potentially large groups of robots that have to interact with one another to either carry out a collaborative task or to compete with one another. So both collaboration and competition are things that I'm interested in. So I'm going to talk about two projects that are ongoing in my lab currently. And actually, both of these projects were discussed a little bit in the lightning session and the poster session earlier. So some of this may look familiar. So we're interested in collaboration, and in particular in collaborative manipulation. And our inspiration is in ants. So you may have seen that a group of ants can cooperatively move something much larger than themselves, something too large for any single ant to move on its own. And they can accomplish this manipulation somehow without using a Wi-Fi network or without talking to one another. Somehow they do it through feel, right? And so we have taken that inspiration and developed an algorithm that allows a group of robots to do exactly this, to collaborate in moving something that's much larger than any one of them individually. And you can see a simulation of our little symbolic ant robots, which are rendered as spheres, cooperating to move a piano. And then I'm going to talk about competition, and in particular UAV racing, or any kind of racing situation. It could be cars, could be UAVs, whatever. But the key to this competition is that it's a race, and the only interaction that's allowed between the racers is through collision. So you might imagine that's true with cars, that's true with airplanes. The only reason that a race is interesting with 2 cars and not interesting with 1 is because the 2 cars can collide. There's a threat of collision. That's the only way they interact with one another. And so we saw this video earlier, the lightning round, and what I want to point out here is not so much the incredible agility of the UAV, it is certainly impressive, and the collision avoidance, that's impressive. What I want to point out here is the competition between the different pilots. You can see the little colored blobs are the other UAVs, and the pilots are pretty fierce, and sometimes they even hit each other. This is the threat of collision that makes this an interesting competition, and that's what we're focusing on. So let's talk first about cooperative manipulation. So our algorithm essentially harnesses the object itself as a medium for communication. So it's the motion of the object that contains all of the information necessary to synchronize the feedback controllers of all of the robots. And in particular, our setup has an arbitrary number of followers. It's highly scalable. I mean, we're only limited by the physical number of robots we can fit around the object we're trying to manipulate. Lots of followers, and then a single leader. That leader may be a robot, it may be a teleoperated robot, or it may actually be a human being. So you can imagine I'm trying to move this thing, maybe it's very heavy, and I have 100 helper robots, and I can just pull it around with my fingers, and the helper robots essentially amplify the force that I'm applying to help me maneuver it. So the way this works is we're trying to essentially reach a consensus among the forces applied by all of the robots. And you can see this displayed here. So how does this thing work? Never mind. So you can see there's the uncoordinated forces. The thing is not going to move in any particular direction. And then you have the coordinated forces. They're aligned in their direction, and so they're all going to help one another to move in a coherent direction. So essentially what we've discovered is that if you take an algorithm that actually does require communication. It's a well-known algorithm in multi-agent control. It's called consensus. There's a lot of research activity in the control community on consensus. And the basic concept of consensus is you keep talking to your neighbors and you keep averaging the results of your neighbors with your own result in a dynamic fashion, and eventually everybody reaches an agreement. We want to do that with forces, but this requires, at least on the surface, some kind of communication for me to tell you what my force is and vice versa. So what we've discovered is that if you take the consensus law, which is the first equation shown there, and then you do a little bit of algebra, the thing that you don't know, which is the sum of all of the other applied forces, can be achieved by replacing that unknown term with Newton's second law. So you can, instead of communicating the forces from the other robots, you can feel the effect of the forces from the other robots by sensing the motion of the object. And that's the key insight. So in other words, we can communicate just by feeling the reaction forces between ourselves and the object. So we've implemented this in a number of hardware platforms. I'll just show you one. So this is a little modified M3 Pi robot, and you can see he cannot alone transport this box. But when we have multiple of these guys acting together, they can cooperate to transport the box. There's no communication network here, as I said. You just have the one leader, who's the one in the front, and then the 3 followers who are helping the box to move along by pushing. And here, the trajectory was predetermined and executed by the leader. The followers are just following. But then we can also have the trajectory teleoperated by a user, as I mentioned initially, and we can also have the trajectory determined by a human operator. Now, of course, John, who's the real brains behind this, and the guy pulling the box, he could actually pull this box on his own, but you'll have to trust me that the robots are actually helping him to do this. Okay, so now let's transition. This was all about collaboration. Let's talk a little bit about competition. And in particular, we're going to talk about drone racing. This is mostly the work of my postdoc, Ricardo Spica. The idea is you've got 2 drones. They're going around a track, and you just want to cross the finish line before the other guy, right? So it happens to be a zero-sum game. The fact that it's a zero-sum game is just displayed through the fact that as long as I'm ahead of you, it doesn't matter what my time is on the clock. The only thing that matters is if I'm ahead of you, I'm going to win. So it's just the distance between the 2 of us that's the objective for both of us. And a typical way to apply game theory to competitive scenarios like this, which has been studied pretty extensively, is called a Stackelberg game. And a Stackelberg game is usually used for a sort of extra safe strategy. It means that you assume that your adversary is extremely powerful and knows what you're going to do before you actually do it, and then you do the only thing that you can do that's safe in the face of this extra powerful adversary. And so in the case of racing, this is totally inadequate. The only thing you're going to be able to do is turn around and run the other way, because the other drone can always chase you down and block you. So you can't be so scared of collisions. You have to be able to calculate that the other guy doesn't want to collide either. And so the concept here of both agents wanting to avoid collisions, this is the concept of a Nash equilibrium, which is a different style of game that hasn't been studied quite as much in differential games. So the idea between a Nash-style game is nobody can unilaterally change their trajectory and improve the score. And so it's very difficult in general to find Nash equilibria, but the way that we're proposing to do this is through iteration. So we plan one trajectory, and then we plan the other, and then we plan another one again and plan the other. Every drone is doing this sequential planning for the other drone. Okay, so I'm simulating the other guy, I'm planning my own trajectory, then his, then mine, and so on, back and forth. And we have to do this very quickly because we want to do this online in an MPC fashion. So here's what the algorithm looks like. It's just a repetitive path planning procedure. Again, I plan for myself, then the other guy conditioned on my path, and then I plan myself again, conditioned on his path, and so on. And what we can prove about this algorithm is that if it converges, we don't know for sure that it does, but it seems to in simulation. If it converges to the necessary conditions for a Nash equilibrium. So Nash equilibria don't just, you don't throw out conditions for Nash equilibria as you walk down the street. They're quite difficult things to prove, so this is not a bad result. So I'm going to skip the details in the interest of time, but to give you a high-level intuition, we characterize the other guy's trajectory, in particular the sensitivity of the other guy's trajectory, as a function of our own trajectory. So we essentially look at how, when we change our trajectory, how it shifts the other guy's optimal trajectory, and we embed that inside of our objective function for a sequential convex program. And so when we plan our trajectory by solving this sequential convex program, we assume that we're going to shift the other guy's result as well. And that's just one of the iterations, and then we mirror that same algorithm on the other guy, and we go back and forth until convergence. And we can actually do this at 20 milliseconds. It doesn't take long at all to complete this, this series of iterations. So I'll show you what one of these games looks like. You can see here, each quadrotor has its path planned, but each quadrotor has two paths emanating from it, one that it planned for itself and one that its adversary is expecting it to execute. Sometimes these paths are aligned and sometimes they're not, because we're solving this iterative thing with potentially multiple equilibria. But what is interesting to note here is that there's real interaction due to the threat of collision. They block each other. There's real strategy going on. And we've run this game theoretic controller against a more naive model predictive controller where there's no game interaction. And the short story is that we do much better than the model predictive controller. And we've also competed against a more simplistic reactive version, which is called reciprocal velocity obstacles, and we just completely destroy the reciprocal velocity obstacle version. We are looking at implementing this on autonomous cars, and we have just completed a hardware-in-the-loop execution of this game theoretic controller with a full-scale autonomous car. You only see one car here because the other car is actually simulated. Maybe next year I'll show you two cars full-scale that are competing with one another. Okay, thank you.
Thank you, Mac.